Okay, let's get started. So welcome back to this week's lectures as part of our course on attosecond science and technology, which we bring to you from the Indian Institutes of Technology in Madras and Tirupati. We are now going into further lectures of this module on measuring the shortest of pulses. So, our key references remain predominantly the same, but the first three in the list are of particular importance for this section. And of course, as always, credits to Professor Trebino, who in fact is a pioneer in the field of ultra short pulse metrology, and we will see some of the nice work that was essentially co-invented or invented from his group and that of other experts. So, what are we up to here? The statement of the problem and the challenge, if you wish, have been well laid out in the last couple of lectures, and we have kind of understood that self-referencing methods or autocorrelation methods are going to be the way forward when it comes to measuring the shortest pulses that we can create in a controlled, repeatable way in a laboratory. In this lecture, we will pay particular attention to second and third order autocorrelation, examine the needs and the motivations behind this, but also ask ourselves the question, is this everything there is to measuring the shortest pulses, and is doing autocorrelation ultimately sufficient or enough, and what do we even mean by enough or sufficient? We need to understand this very well in a technical, quantitative and even mathematical framework and manner. So, a quick 3-minute recap on the measurement problem itself for ultra short pulses. We need to start measuring ultra short pulses, we know this, and we realize that ideally speaking this is achieved by using the pulse itself, making 2 copies of it and converting temporal information into spatial information, or sort of mapping time to space using a delay component, which is a delay line, and then doing something with it that is to use one copy as a reference and the other copy as the test object. While we neither know the reference well nor the test object well, we are equally ignorant about both, but we just know that two fairly you can say identical copies, identical within quotes, one can ask that we qualify this better. It need not actually be identical copies always. We need to know something about these pulses, have some physical model to have capture their essential features, and then we can cross them in a say a medium of interest, which we will say more about in today's lectures, or even place a detector right here where they interfere with each other, and then do some measurement, most importantly as a function of delay. By moving this stage, this is a mobile stage, back and forth, we will be able to control the delay that exists in time between these two pulses, owing to the fact that we are controlling the optical paths or the difference in optical paths between these two pulses with a when referenced to both the source as well as the detector ultimately. So, in that sense, we essentially continue to subscribe to this picture of the time varying electric field of an ultra short pulse or any light pulse or electromagnetic pulse, and we have an instantaneous frequency defined in order to take care of the fact that the frequency can vary even within a pulse itself, that is underneath the region of the envelope where the amplitude is significant, and as a function of time both the instantaneous phase phi of t and the instantaneous frequency can vary. the variation of the frequency need not be just linear, it could be quadratic, it could be even cubic or whatever, as well as the phase needn't always be parabolic as we are trying to represent here, it could be even more complex. If the phase variation with time is quadratic or parabolic and the frequency variation in time is linear as a consequence, then the pulse is said to be linearly chirped, right. Now, all we can do in the laboratory is do in some sense spatial domain measurements, and since a full characterization of the pulse would involve, as we have reiterated in earlier discussions too, both a knowledge of the amplitude, particularly the envelope, and a knowledge of the phase function in time, right, or equivalently the amplitude in the frequency domain and the phase in the spectral domain, spectral amplitude and spectral phase, or temporal amplitude and temporal phase. If we have a complete knowledge of either pair, we can Fourier transform to go from one domain to the other seamlessly and without any loss of information, right. So, as a consequence, we would prefer to do these measurements in the spectral domain, because in the temporal domain we have very little control over what we can do. In fact, one would involve a complete measurement would involve both a delay measurement and a spectral measurement both. So, we need to get a hang of this spectrometer, which is basically a device which takes an input and converts the spectral information in this input, which is present in every part of this beam before it goes through this dispersive element, which is the grating. The dispersive element spatially separates the various constituent frequencies or wavelengths and projects them onto preordained points on the plane of a detector, which simply records a spatial variation of a signal which is incident on it. In fact, this detector does not need to know anything about the color of the light that is coming through. It is essentially a black, grey, white type of detector which is totally agnostic to the spectral features. Okay. So, this is therefore a detector which is merely playing a passive role, in that it is going to give an output signal which is linear in its response to the input amplitude at every pixel, be it a single pixel detector which you can scan across this plane, or it could be a multi-pixel detector like a camera. So, so what we seek to do is a one-dimensional sort of phase retrieval, that is to say we measure spectra which is S of omega, but then the whole field itself is described as a product of S of omega or its square root and the complex exponent of phi of omega, the spectral phase, which we do not really which we do not discern from a spectral measurement in itself, but which we seek to determine in this metrology problem. In 1D this is not even theoretically possible, it seems, but then in 2D it becomes possible. That is the interesting part. But we developed a mathematical model for the detector where we said the signal measured by a photodetector is essentially a time integral over an extremely long duration of time, much longer than anything that concerns the oscillations of the electric field or even the rise and fall of the envelope function describing this electric field. And this infinite time integral is what represents this infinitely slow detector. Okay. So, we even made some little back of the envelope calculations which said that the age of the universe to the human heartbeat is an 18 orders of magnitude. So, an attosecond pulse to a second is also 18 orders of magnitude. So, if we have a detector that responds anything like on human time scales of a second or maybe a fraction of a second, that is already like on a comparative scale extraordinarily slow, right, in terms of the what we want versus how fast or slow the response is. So, detectors have typically rise fall times of nanoseconds. We saw this, we convert time domain information to spatial domain information using a delay stage. We have a reflective element which is put on a translation stage. When translated by an amount L either forward or backward, assume this is a retraction by a length L, then it introduces a delay of plus twice the length of the retraction length L divided by C, and a rule of thumb is that light travels 300 micrometers in a picosecond or 300 nanometers or 0.3 micrometers in a femtosecond. So, we can produce say delays by moving this stage reliably with sufficient accuracy, repeatability and precision. Okay. And in order to retroreflect beams, we have a cube corner which essentially involves 3 reflections, so that it gets rid of any out of plane tilt in the beam. This is a technical matter. We discussed this, that if you want to bounce off a beam from the moon's surface, so to say, you essentially do not want beams which the reflected beam to be anything but very close to being parallel to the incident beam itself. Now, what we then said is the following, that we analyzed the signal that we could produce from a Michelson type interferometer, which is essentially 2 delay lines which are introduced after splitting a beam using a beam splitter. The first beam goes to a mirror, retroreflects, comes back. The second piece goes to a stage which has a mirror which retroreflects the beam, but the optical path in the vertical arm of the interferometer, that is the up down arm, is greater than in this case and in this depiction than the horizontal arm, which is the left right arm of this interferometer. The beam splitter does a good job of recombining these 2 beams, and then these 2 beams are captured by our infinitely slow detector. So, this detector has no sense of time, but then we can perform measurements of the signal on this detector as a function of the delay that we introduce deliberately in one of the arms of the interferometer with respect to the other, which is tau. Now, particularly those of you who are familiar with Michelson interferometer understand that we can do 2 things. A Michelson interferometer signal can have fringes, or it is supposed to have fringes which are bright and dark. In one configuration, these become concentric circular annular rings, if you wish, bright versus dark. I am shading the, let us say, the bright part for the red bright beam. Okay. So, now a fine point, we have depicted here that this is the signal produced by such a Michelson interferometer. A matter of detail, now we can ask whether the detector that is measuring the signal is capturing the intensity variation or the irradiance variation of a point which is within a fringe, or whether it is integrating this entire set of fringes. Okay. Whether it is a spatial integral, say dx dy, over this entire set of fringes. We have 2 options or opportunities. Now, in this description of the Michelson interferometer and fringes, we have presumed that the detector has a pinhole ahead of its photoactive or photosensitive element, so that it essentially monitors the variation of intensity over an area which is smaller than the size of a fringe. So, it could be viewing the central fringe here, the red dot at the center, or the experimenter or the practitioner could have placed it so that it essentially monitors a small region somewhere along one of the rings. It is up to the experimenter. Imagine you could even collect this light using an optical fiber, which essentially looks a single mode fiber could have a core diameter of something like 20 microns or even less, right? And you could place it right there. Okay. So, all these are possibilities, and as the delay stage moves, the signal varies as a function of delay. Now, in this scenario, we have positioned the detector to observe one of these into one of these fringes, bright or dark. One could have placed it even on what I am envisioning to be like a dark fringe, which is a white patch on this figure. Okay. In either case, if the detector views only one of these, it could even be like a slit that is, limiting its the detector's view of only one of these fringes. Then we get a corresponding variation in the amplitude signal, where we see an envelope for this signal and also some kind of oscillations underneath the envelope. This is exactly representative of the envelope and the carrier wave of the pulse itself. This also presumes that the delay stage has taken sufficiently fine steps so that it can sample the a limited optical cycle. If the wavelength of the laser of interest here producing these pulses is, let us say, a popular wavelength like 800 nanometers. So, it is 400 nanometers of a maximum plus a 400 nanometer spread of a minimum. So, the delay stage should ideally have moved in, say, some steps of, it is a wavelength, right. Should have taken maybe steps of something like 100 nanometer step, or even finer, it could be 50 nanometer steps and so on, right. This is something which one has to build up. If we do that, then the math here carries us through, where we say that the signal is made up of a sum of the two electric fields, E of t and E of t minus tau, the piece that is coming delayed. Okay. But then we have a negative sign here, which is owing to an extra phase factor introduced by the beam splitter here, which is why E1 plus E2 becomes E of t minus E of t minus tau. That is a matter of technical detail about the Michelson, which we discussed, which I said we would discuss in the post class discussion. But even if you have a plus sign here, the physics of the result is not going to change. In some literature you may even find a plus sign, but it is just a phase factor which will somewhere drop off. So, do not worry too much about it, but the point being that as a consequence of this, you get two pieces of the whole signal, three pieces rather. First is E of t, the electric field coming in from the horizontal arm, E of t minus tau, electric field from the vertical arm, right. And then the interference, the delay variation itself comes from this sort of cross term, where we multiply E of t and E of t minus tau. Okay. If it so happens that throughout the integration, it happens that for most values of t, either E of t or E of t minus tau, only one of the pulses is present, the other guy is having 0 at that particular value of t, right. So, then this term can even become null or 0 if the two pulses are separated substantially far apart in time, in which case the entire signal would be a sum of the contribution from arm 1 and arm 2. You are integrating this indefinitely over time, t from minus infinity to infinity, or in practical scenarios a whole range of time itself. So, this becomes a number which is the irradiance in path 1, irradiance in path 2. What we are interested in is the variation in the signal in a small range of time, which is about the 0 of delay, which is where the two pulses overlap one on top of the other. Okay. So, this is an autocorrelation of the electric field. As I said, if I have sufficient resolution in time steps of my delay stage, which is essentially spatial steps of the order of, in this case, if the laser wavelength is 0.8 microns or micrometers or 800 nanometers, then you want small steps and you get an autocorrelation of the autocorrelation signal, which is gamma of tau. This is a second I mean, we are autocorrelating to signals, which is a linear autocorrelation. So, the superscript is 2 here. This happens to be the Fourier transform of the spectrum of the pulse. It just happens to be that. We discussed this at some length in the previous lecture.